So section 7.2 is a section called Exponential Equations. Exponential means there's an x in an exponent or in multiple exponents. Equations means the problems have equal signs. And basically we're going to come up with a strategy to find a number that we could change the x to, so that if I plug it back into the original problem, that both sides equal each other. And in order to do this section for the problems you just can't look at and do in your head, you're going to need to know some powers of some prime numbers. So I'm going to probably pull out this sheet a lot. I need to know powers of 2, 3, 5, and 7. I don't think I need to know any other powers for this section. If I need them, I'll write them down. But I'm going to pull out this sheet all the time. I just wrote this up a second ago. We're going to try to do all the odds in this section. So, all the odds. Which means I should try to do all the evens. The first few problems on this sheet I probably could do without any algebra, but eventually you won't be able to look at the problems and know what the answer is, and the algebra is going to be important. And the algebra for each one of these problems is any number that's not prime. I'm going to find its prime factoring. So if I was doing problem 2, I know the answer is 3 because I know the powers of 3. But the technical way to do this is to any number that's not prime, I'm going to find its prime factoring. And the prime factoring for 27 is 3 cubed. So what I'm going to do in problem 2 is I'm going to do the prime factoring for 27, which is the number that wasn't prime. And in each of the problems in this section, I'm going to be able to write each side with the same base. And once I can get both sides written with the same base, I can drop the bases. In this case, I'm going to drop the base of 3. Bases of 3. And set the exponents equal to each other. Sometimes that's all I need to do when the exponent is just an x. If the exponent's more than just an x, then after I set the exponents equal to each other, I'll need to do the algebra to isolate the x. I claim in problem 2 that that's the answer, and I can always check. I don't have to check these. If I don't make a mistake, my answer is going to work perfectly. There aren't going to be any extraneous solutions. The original problem was 3 to the x equal to 27. For my answer to be correct, if I change the x to 3 and simplify that left-hand side, the left-hand side has to match up with the right-hand side. There are many ways to do these problems. The way that I'm teaching is the way that will work regardless of how complicated the problems get. If I was trying to do problem 4, I know the answer is 2 because I know that 4 squared is 16. That's fine. If you can know the answer by just looking at it, more power to you. But as the problems get more complicated, you won't be able to. So for my attack, any number that's not prime, I'm going to do a prime factor tree for, and I have the prime factor trees for it. So for this problem, I'm going to do a prime factor tree for 16. 16 is 2 to the 4th power. And I'm going to do a prime factor tree for 4, but because the 4 already has an exponent, I'm going to do my prime factoring for 4 and put it in a parentheses. 4 is 2 squared. So any number that's not prime, I'm going to do a prime factor tree for. 16 is 2 to the 4th. 4 is 2 squared. If a number that I'm doing a prime factor tree for already has an exponent, usually I do the prime factoring, I put it in a parentheses, and then to clear the parentheses, I multiply. So on the left-hand side here, the parentheses that I temporarily put in, I'm going to clear by multiplying the exponents of 2 and x. And this is way overkill for this, but as the problems get more complicated, this strategy is going to be what we need. So now I have the problems with the both sides written with the same base. Once we can get the bases on each side the same, I'm going to drop the base on both sides. I guess it would be bases of 2 and set the exponents equal to each other. The exponent on the left-hand side is 2x, on the right side is 4. I don't have an answer yet here because the x isn't isolated. To get the answer of 2 that I knew even before I did any algebra, I technically would have to divide by 2. I can check every one of these. That would avoid me making math errors. But it's not technically necessary because there isn't extraneous solutions to worry about if I don't make a math error. So for this one, the checking works perfectly. Every one of the problems I'm going to attack the same way. Any number that's not prime, I'm going to do a prime factor tree for, and it's going to be one of these. It's either going to be a power of 2, a power of 3, a power of 5, or a power of 7. If I made it like powers of 6 or powers of non-prime numbers, it might get too confusing, and there's a way to solve using something more complicated called logarithms when the bases aren't such nice, like 2, 3, 5, 7, nice prime numbers. So I'm going to be real consistent, and some of these problems you might be able to look at and just know what the answer is, and that's fine. All right, so I'm going to start with 6. You can work on 5 if you care to. 6, on the left-hand side, the base 2 is a prime number. I'm not going to do anything to the left-hand side. The right-hand side, I'm going to do a prime factoring for 32, and 32 is 2 to the 5th power. Because I have the bases the same, if I can get both sides on the opposite side of the equal sign to have the same bases, I can drop the bases and set the exponents equal to each other. So algebraically in problem 6, I can make both sides have a base of 2. Once I can get both sides written with the same base, I can drop the bases and set the exponents equal to each other and do the algebra that's necessary to get the x isolated. So for problem 6, I think my answer is 4. If I wanted to check, the original problem is 2 to the x plus 1 equals 32. I should make sure that 2 to the 4 plus 1 equals 32. And it's super easy to do. 2 exponent 4 plus 1, and that gives me 32 equals to 32. Don't have to check these, but it's not a bad idea to check them. Let's do 7 together. I'll skip 8. So 7 is 2 to the 4 minus x. I'm going to emphasize it's 4 minus 1x equals 64. 2 is a prime number. I'm not going to worry about it. 64 isn't prime, so I'm going to write it as 2 to the 6th power. So this gives me 2 to the 4 minus 1x equals 2 to the 6th. All these problems are written so that with 1 or 2 steps you can write both sides with the same base. If you get the bases the same, then you can drop the bases and set the exponents equal to each other, and then do the algebra to isolate the x. In problem 7, it's going to be 2 steps. I'm going to minus 4, and then divide by negative 1. So minusing 4 would give me negative 1x equals to 2. And then I'll divide by negative 1 and get x equal to negative 2 for my answer for number 7. The checking part, it's not terribly hard to do. The original problem is 2 to the 4 minus x equals to 64. I should see if 2 to the 4 minus negative 2 power equals 64. And the negative 2 I put in a parentheses just because I have a double negative there. So for checking 2 exponent 4 minus parentheses negative 2 power, and that gives me 64. So I get 64 equal to 64, perfectly checked. There's just a couple tricks in this section, and it comes up on 10, 11, and 12. If a number has an exponent and you need to do a prime factoring for it, you should do it in a parentheses. So if I was doing problem 10, the 27 to the x equals to 3, I'm going to do a prime factoring for 27, and because it already has an exponent, I'm going to put it in a parentheses. 27, its prime factoring is 3 cubed. So the left-hand side, I'm going to write in a parentheses 3 cubed to the old exponent of x. And on the right-hand side, that 3 doesn't have an exponent. It has an implied exponent of 1. To clear the parentheses on my left-hand side, I'm going to multiply the exponents and get 3 to the 3x power on the left-hand side. The right-hand side's going to say 3 to the first. Once I can get both sides written with the same base, I can drop the bases and set the exponents equal to each other, and then do the algebra to isolate the x. The algebra to isolate the x here is just dividing by 3. For problem 10, my answer is going to be x equal to 1/3. If I wanted to check, the original problem says 27 to the x equals to 3. I should be able to make sure that 27 to the 1/3 power equals to 3 to make sure I haven't made a mistake. So just simply 27 exponent fraction 1/3 power. That'll simplify the left-hand side and make so I know I didn't make a mistake. Let's do 11 together for the heck of it. You can pause the video and do 11 if you want. For 11, I'm going to do a prime factoring for 16. It already has an exponent, so the prime factoring I'm going to put in the parentheses. 16 is 2 to the 4th power. I'm going to do a prime factoring for 4, which is 2 squared. I can do these problems differently. If you're getting the right answer and you're not doing them exactly the same as me, there are at least 2 or 3 ways to do most of these problems. I'm just doing the way that I can do every problem the same way, and which I think makes it easier as the problems get harder. On the left-hand side, because the 16 had an exponent, I put a parentheses. Now I'm going to multiply the 4 and the x to clear the parentheses. Once I get both sides written with the same base, I set the exponents equal to each other and I drop the base and do the algebra that's necessary to isolate the x. In this case, it's dividing by 4. On the left-hand side, when I divide by 4, I just get the x. On the right side, 2 over 4 is 1/2. I should be able to check all of these. The original problem said 16 to the x equals to 4. I should be able to make sure that 16 to the 1/2 power equals to 4. So 16 exponent fraction 1/2 power, and perfectly, that works perfect. So I've got my answer, I checked my answer. I'll do 14 next. 14 has 125, which is 5 cubed. 625, which is 5 to the 4th. I'm going to do prime factorings for any number that's not prime. If a number already has an exponent, I do the prime factoring inside of parentheses. So this 125 had an exponent. Its prime factoring I'm going to put inside of parentheses. The 625 doesn't have an exponent. I don't need a parentheses on the right-hand side. I've set all of these problems up so that the prime factorings will have the same base. I'm going to clear the parentheses. And to clear this parentheses, I have to multiply 3 by x and 3 by 2 in problem 14. So in problem 14, the left-hand side's exponent should be 3x plus 6. Once you get both sides written with the same base, you just drop the bases and set the exponents equal to each other, and then do the algebra to isolate the x. So in problem 14, you get 3x plus 6 equals to 4. I'm going to minus 6 from both sides, and get 3x equals to negative 2. And then I'm going to divide by 3. And I'm going to get a negative answer that's also a fraction. That means I should really check this because I don't usually make answers like that. But I think my answer is x equals to negative 2/3. I'm going to check it just to make sure I haven't messed up. The original problem was 125 to the x plus 2 equals to 625. I should see if 125 to the negative 2/3, wow, plus 2, that doesn't even make sense. I have to have a mistake here. 5 cubed, 5 to the 4th, 3x plus 6 equals, I just don't see a mistake. I'm going to check this. I'm probably going to say I have a mistake. I just don't see the mistake. So 125 exponent fraction negative 2/3 plus 2 hit equals, and it worked. It surprised me. I just was trying to do it in my head and it just wasn't working. But this is what you can do every time. You could take the answer that you get, change the x in the original problem back to the answer, and simplify. Make sure both sides come out to be the same. The next few problems, we're going to start getting into the world of fractions, and we're going to need to use this rule, something like this: 1 over x to the n equals x to the negative n power. So these problems don't solve so well when we have fractions, and I'm going to use a strategy to make the fractions to have negative exponents. It's going to make it easier actually to work with negative exponents than it does fractions. In problem 16, the fraction is 1 over 2 to the first power. It's a prime number. I won't worry about doing its prime factor tree. 8 is not a prime number. I'm going to do its prime factor tree and write it as 2 cubed. The left-hand side is 1 over 2 to the first power. I'm going to change the left-hand side into 2 to the negative 1 power. So a fraction with a 1 in the numerator can be written with a negative exponent if I just take the denominator, write it without a fraction with the exponent positive. That's using kind of this rule. Now I'm going to clear the parentheses by multiplying the exponents, and I'm going to get 2 to the negative 1 times x equals 2 cubed. Now both sides have the same base, so I'm going to drop the bases and set the exponents equal to each other and do the algebra to solve for x, and the algebra to solve for x is just dividing by negative 1. This is going to give me my answer, if I haven't messed up, of x equals to negative 3. I'm going to check to make sure in my original problem of 1/2 to the x equals to 8, make sure that 1/2 to the negative 3 equals 8. So let me check it real quickly. Parentheses, fraction 1 over 2, parentheses, exponent negative 3, and that gives me perfectly 8 equals to 8. So a big trick for this, the last trick, is if we have fractions, we need to make fractions into negative exponents. Let's maybe do 17 together. On 17, this is 1 over 2 to the first power, all to the x, equals 16. The left-hand side I'm going to have a negative exponent. The right-hand side I'm going to do prime factoring for 16, which is 2 to the 4th. On the left-hand side, I'm going to multiply my exponents to clear the parentheses. Now that I have both sides written with the same base, I drop the bases of 2 and set the exponents equal to each other. And I do the algebra to isolate the x, and the algebra is just dividing both sides by negative 1. And my answer is going to be negative 4. And I just won't check this because I think it's going to check. I'm trying to get one more problem in this video. And I better do 19 because it's not like the other problems. On 19, both 256 and 4 are prime numbers. I'm going to do a prime factoring for both. 4 is 2 squared. So in 19, I'm going to make the left side 1 over 2 squared. And 256 is 2 to the 8th. So I get 1 over 2 squared to the x equals 2 to the 8th. I'm going to make the fraction into a negative exponent. So the negative exponent on the left-hand side is going to be 2 to the negative 2 power. I'm going to clear the parentheses by multiplying the exponents and get 2 to the negative 2x power equals 2 to the 8th. Now that the bases are the same, I'm going to drop the bases and set the exponents equal to each other and get negative 2x equals to 8. And then I'm going to do the algebra to get the x solved for, which is just dividing by 2. This is going to give me x equal to negative 4. I think that's my answer. I'm going to run really short. I'm going to try to check this and go, is parentheses 1/4 parentheses exponent negative 4 power, does that equal 256? When I plugged it in, it does. I'm going to pause it and do a part 2 now because I'm kind of out of time.